Hi there chemistry students, we have an A-level chemistry year 2 question here, a past paper question from AQA on thermodynamics. So the first part of this question refers to the Born-Haber cycle given below. You might want to take a photograph of that. Next up, we are given a table with some standard enthalpy changes. Once again, you will need this for the next part of the question. Okay, so here's our first task. We need to insert the species including state symbols on the appropriate lines. So let's take the bottom left hand line just above cesium iodide solid. That's cesium solid and a half iodine gas. The top line is cesium plus gas plus an electron plus iodine atoms gas. You need to memorize the definitions for the standard enthalpy changes. We're going to need that for the remainder of the question. So if we just take the bottom left hand side, the cesium solid plus a half I2 gas going to cesium iodide solid, that represents the enthalpy of formation of cesium iodide. I won't go through all of them, but the top one, the cesium gas going to cesium plus gas plus an electron with the iodine atoms remaining as iodine atoms, that represents the first ionization energy of cesium. Okay, so next we have the calculation, a pretty standard Born-Haber cycle calculation. We need to link the standard enthalpy changes and the data to the various processes on the Born-Haber cycle given. We're looking for X, which is the enthalpy of atomization of iodine, in which we start with the elements in its standard state and we need to form 1 mole of gaseous atoms. We can go round in a clockwise or an anti-clockwise direction, so I've chosen the clockwise route, but the plus 376 is an endothermic change. We need to put energy in. This enthalpy change, the plus 376, represents the first ionization energy of cesium. We make 1 mole of cesium gaseous ions, 1 plus ions, by starting with 1 mole of gaseous cesium atoms by removing 1 mole of electrons. Minus 314, this represents the electron affinity, the first electron affinity of iodine. So we have added 1 mole of electrons to 1 mole of gaseous atoms to make 1 mole of gaseous iodide ions. Minus 585, that represents the enthalpy of lattice formation of cesium iodide. We form 1 mole of the ionic lattice from its constituent gaseous ions. It's worthwhile noting that the minus 314 for the electron affinity is an exothermic process due to the attraction between the negative electrons and the positive nuclei. Minus 585, the enthalpy of lattice formation, is also exothermic, again because there's an attraction between the cesium plus and iodide minus ions. If we take the next minus 337, the next standard enthalpy change, that's pointing downwards from the cesium solid and the half iodine solid. That is the enthalpy of formation of cesium iodide, in which we have formed 1 mole of the cesium iodide substance from its constituent elements in their standard states. And the final enthalpy change, the plus 79, if we take a look at the state symbols there, we can see we've gone from cesium solid to cesium gas. So we have atomized the cesium, again an endothermic process because we have to put energy in to break the solid apart to make the gaseous atoms from the solid. So X, if we remember our Hess's law, the enthalpy change is independent of the route taken. So X, the arrow there is pointing upwards. If we go in the opposite direction, we go against the plus 79, so minus plus 79. We go with the minus 337, so plus minus 337. We go against the minus 585, so minus 585. We go against the minus 314, so that's minus 314. and we go against the plus 376. So I've tried to illustrate why we add and subtract the negative numbers by using brackets there. Mistakes are commonly made by getting muddled up with directed numbers, so it pays to take care of these. If you plug those numbers into your calculator, you will find that the enthalpy change is plus 107 kilojoules per mole. The sign is important, as are the units. Okay, next part of the question is just a factual recall. It's about a comparison of the value obtained by calculation compared to the perfect ionic model. So some substances can have some degree of what we call covalent character, even though they are ionic. There's a spectrum of bonds. So we need to talk about bonding. If the perfect ionic model gives a value which is close to what we can calculate, it tells us that the bonding is going to be very ionic, almost perfectly ionic. If it was far away, we could say that the substance contains or exhibits an awful lot of covalent character. The fact that minus 585 kilojoules per mole is very close to minus 582 tells us that caesium iodide is almost purely ionic. Put that another way, it has very little covalent character. Okay, just to finish off, it seems that we've got a Gibbs free energy question here, so we need to show that this reaction is not feasible at 298. So, not feasible, what does that tell us? Well, delta G has to be positive. If the Gibbs free energy is greater than or equal to 0, the reaction is not feasible. So we can work out values for delta S using the data given in the table. It's also good to start off with the equation for delta G. So the entropy change is the entropy, or the sum of the entropy of the products minus the sum of the entropy for the reactants, and delta G is equal to delta H minus T delta Fs. We just had to multiply the molar quantities of each of the substances, and that gives us a value of 82.8 plus a half times the 117. That's for the reactants, the products rather, and subtract the reactants, so that's minus 130, and that gives us a result there of plus 11.3. Now units are crucial here, joules per mole per Kelvin, because in the next equation, the delta G, we have got to put in a value for delta H given to us in the question, and if you look carefully, that's got units of kilojoules per mole. So we need to be consistent. So I have changed the entropy to kilojoules per mole per Kelvin. I could have changed the delta H to joules per mole, but I'd have to be consistent, either using kilojoules per mole for enthalpy or joules per mole, depending on what I chose for entropy. Put the numbers in, and that gives us a result of plus 334 kilojoules per mole, which is indeed positive, which tells us that the reaction is not feasible at this temperature.